We now study line integrals. The single integrals that we have studied so far have been over some interval a to b. That is, we've been integrating over an axis. We now develop a way to integrate over any curve. Such an integral is called a line integral or a path integral. So you may often hear me refer to it as a path integral, and this is simply because we're integrating really over a path instead of a line. So we consider two types of path integral: a scalar function and a vector function. We begin by studying a scalar function. Now we let C be a curve. Specifically, let's say it is this curve over here. Now what we do is we divide C into n consecutive arcs, C1 up through Cn. Choose a sample point P sub I star in each arc C sub I. Notice that nowhere are we restricting that each arc has to have equal length. Right? In fact, if you see this one, this C sub I is longer than all the others, and that's perfectly fine. Then we form the Riemann sum I equals 1 to n, f of P sub I star times delta S sub I, where delta S sub I is the length of the curve C sub I. The line integral over C is then the limit of this sum. Let f be a function with a domain that includes the smooth curve C. The scalar line integral of f along C is defined as this limit and is represented this way. So integral along C of f of x, y, z ds, as long as this limit exists. Notice that if the scalar function we are integrating is simply the unit function, we get a length, we get the length of the curve. So we get the arc length of the curve. Right? And that's stated here. The arc length of the curve C is simply the integral along C ds. So we want to find a way to compute a line integral. So suppose that r of t is x of t, y of t, z of t for a less than or equal to t less than or equal to b is a parameterization of a smooth curve C. Then r prime of t, which is x prime of t, y prime of t, z of t, is continuous for all t in a to b. Now recall that the arc length of a parametric curve over the interval t0 to t1 is given by this integral right here. So we have that delta S sub I is the integral from t sub I minus 1 to t sub I of the norm of r prime of t dt. If delta t sub I is small enough, then this norm is approximately a constant. And so we can approximate delta S sub I as the norm of r prime of t times delta t sub I. If we now pass this sum through the limit as the norm of delta S sub I approaches 0, so remember this is just the maximum of delta S sub I, it converges to this integral from a to b, f of r of t times the norm of r prime of t dt. So we're going to evaluate the line integral x squared plus y squared plus z, where the curve that we're integrating over is the helix r of t equals cosine of t sine dt for 0 less than or equal to t, less than or equal to 2 pi. All right. First, let's find r prime. That is just negative sine of t, cosine of t, and 1. That means that the norm of r prime is the square root of sine squared t plus cosine squared t plus 1, which is just the square root of 2. Now we have to evaluate f of x, y, z at r. Okay, so f of r of t would be cosine squared t plus sine squared t plus t, so this is just t plus 1. Therefore, the integral over the curve of x squared plus y squared plus z ds is the integral from 0 to 2 pi of t plus 1 times the square root of 2 dt. So we'll get square root of 2 times t squared over 2 plus t evaluated from t equals 0 to 2 pi. This will give us the square root of 2 times 2 pi squared plus 2 pi. Or we can factor out a 2 pi and be left with pi plus 1. Let's look at this one. A wire has a shape that can be modeled with parameterization given here for 0 less than equal to t less than equal to 4 pi. We want to find the length of this wire. Now remember, arc length of a curve is just the line integral of that curve, or over that curve, ds. Alright, we need r prime of t. So that is negative sine, cosine, and then 1 over 2 root t. Take the magnitude of it. We get the square root of sine squared plus cosine squared plus 1 over 4t. This will equal the square root of 1 plus the quarter t inverse. We want to simplify this, so combine it. We'll have 4t plus 1 over 4t. So our arc length will be the integral from 0 to 4 pi of the square root of 4t plus 1 over 4t dt. And with the aid of technology, we can find that this is 1/4 times the natural log of the square root of 16 pi plus 1 plus 4 times the square root of pi, and then plus the square root of 16 pi squared plus pi. Now we look at line integrals of a vector function. An important difference between scalar line integrals and a vector line integral is that the vector line integral depends on the direction along the curve. So if we think of a vector line integral's work, this makes sense. The work performed going down a mountain is the negative of the work performed going up the mountain. It's easier to go down a mountain than it is to go up a mountain. A specified direction along a curve C is called an orientation for the curve. And with an orientation, C is called an oriented curve. We refer to the specified direction as the positive direction along C and the opposite direction as the negative direction. If we let t denote the unit tangent vector at a point P on C pointing in the positive direction, the tangential component of f at t is given by f dot t, which after some algebra will be the norm of f times the cosine of theta, where theta is the angle between f and t. The vector line integral is the scalar function f dot t. So that's our definition. The line integral of a vector field f along an oriented curve c is the scalar line integral along c of f dot t ds. But we can express t ds as the vector differential dr. This allows us to rewrite the line integral as the line integral along c of f dot dr. Since this is now a scalar line integral, we can use parameterizations to evaluate it. There is one important difference. The parameterization must be positively oriented. That is, r must traverse c in the positive direction. We will also assume that r prime of t is not 0 over the domain of integration. Then r prime of t is a non-zero tangent vector pointing in the positive direction, and t is r prime over the norm of r prime. Now in terms of arc length, or the arc length differential, ds is the norm of r prime of t dt. So we can write f dot t ds as f of r dot prime over norm of r prime times the norm of r prime dt, which is just f of r of t dotted with r prime. And that is how we would evaluate if r of t is a positively oriented regular parameterization of an oriented curve c for a less than or equal to t less than or equal to b, then the integral along c of f dot dr is the integral to b f of r of t dotted with r prime of t dt. So let's go ahead and evaluate the integral along c of z y squared x dot dr, where c is parameterized in the positive direction by r of t equals t plus 1 e to the t squared for 0 less than or equal to t less than or equal to 2. So f, which is z y squared x, this implies that f of r is t squared e to the 2t t plus 1. Oops, that one implies. We also have that r prime is 1 e to the t 2t. So we now want f of r dotted with r prime and dt, right? So this is going to be t squared e to the 2t t plus 1 dotted with 1 e to the t 2t dt. This is then going to be 3t squared plus 2t plus e to the 3t dt. All right. So line integral along c of z y squared x dotted with dr is now the integral from 0 to 2 of 3t squared plus 2t plus e to the 3t dt. After some work, we find that this is 35 over 3 plus e to the 6 over 3. Let's look at some properties. Now we can write dr as dx, dy, dz. So with this notation, we can write f dot dr as pdx plus qdy plus rdz. This would allow us to rewrite the line integral as the integral along c of p dx plus q dy plus r dz. So you can see either of these two forms. Now let f and g be continuous vector fields with domains that include the oriented smooth curve c. Then the line integral along c of f plus g dot dr is the line integral along c of f dot dr plus the integral along c of g dot dr. So you can split line integrals across addition. The integral along c of kf dot dr is k times the integral along c of f dot dr. So you can pull scalar constants out of the integral. The integral along negative c f dot dr is the negative integral along c of f dot dr. So if you switch the direction of c, you just multiply the result by -1. And suppose that c is a union of n smooth curves, so c is c1 plus so on and so forth plus cn, then the integral along c of f dot dr is the integral along c1 of f dot dr plus so on and so forth plus the integral of c sub n of f dot dr. So if you split your curve into n subcurves, let's call it, then the line integral becomes the sum of all those individual line integrals. As an example, let's go ahead and look at this. So we want to compute the line integral along c of e to the z, e to the yx, plus, e to the y. This should be a comma here. And then x plus y dot dr, where c is the triangle joining the points 1, 0, 0, 0, and 0, and 0, 0, 1, oriented in the counterclockwise direction when viewed from above. So if we go ahead and sketch this curve, this would be our path. And since it's oriented in a counterclockwise direction when viewed from above, we're going in this direction here. Now this is going to be easiest to do along 3 lines. So we'll call the first line parameterized by r1, 1 minus t, t0, as t ranges from 0 to 1. All right, so how do we determine that? Well, this is the line y equals x minus 1. No, I'm sorry, y equals x plus 1. So we can write it as x equals 1 minus y. No, that's not right. All right, if we draw this, there's the xy plane. We go from 1, 1, right, down to here. So there's our line. So this is the line 1 minus x, y equals 1 minus x. So that can be x equals 1 minus y. That is how we get that curve up there. Using similar arguments, we can write C2 as a parameterization R2 equals 0, 1 minus tt, 0 less than equal to t less than equal to 1. That takes care of this line here. And finally, we can write C3, parameterization R3, t, 0, 1 minus t, all 0 less than equal to t less than equal to 1, and that takes care of this curve. So this is C1 here, C2, C3. Now C is clearly C1 plus C2 plus C3. So the line integral will be the sum of those three line integrals. So we just have to evaluate those three line integrals. So let's start with the line integral of C1. So this is going to be the integral from R1, f of R1 dotted with R1 prime dt. Integral from 0 to 1, e to the 0, e to the t, 1 minus t plus t. Dotted with negative 1, 1, 0. This will give us the integral from 0 to 1, negative 1 plus e to the t dt, and this will wind up giving us e minus 2. Let's now look at the integral along C2. This will be the integral from 0 to 1, f of R2 dotted with R2 prime dt. This is the integral from 0 to 1, e to the t, e to the 1 minus t, 1 minus t, dotted with 0 minus 1, 1 dt. We get the integral from 0 to 1 of negative e to the 1 minus t, I'm sorry, plus 1 minus t dt, and this is 3 halves minus e. If we now look at C3, integral from 0 to 1 of f of R3 dotted with R3 prime. This will give us the integral from 0 to 1, e to the 1 minus t, 1 t dotted with 1, 0, minus 1 dt, which is the integral from 0 to 1 of e to the 1 minus t plus minus t, dt, and that gives e minus 3 halves. Therefore, we can write the path integral along C of f dot dr is e minus 2 plus 3 halves minus e plus e minus 3 halves, which leaves us with e minus 2. We will conclude this video by looking at some applications of path integrals. If we view the curve C as a wire with continuous mass density rho of xyz given in units of mass per unit length, then we can represent the total mass of the wire as m of c equals the line integral along C of rho xyz ds. A similar formula would hold for total charge Q if rho of xyz is the charge density along the wire, given in units of charge per unit length instead of mass density. We can also use line integrals to compute electric potential. When an electric charge is distributed continuously along a curve C with charge density of rho, the charge distribution sets up an electrostatic field E. By Coulomb's law, E is negative del V, where V of P is K times the integral along C of rho divided by d sub P of xyz ds, where this d sub P here denotes the distance from xyz to the point, so it's the distance formula, and K equals 8.99 times 10 to the 9th Newton meter squared per Coulomb squared. That is a universal constant. We call V the electric potential and is defined for all points P that do not lie on C. The units of electric potential is the volt, which is a Newton meter per Coulomb. Now, recall that work refers to the energy expended when a force is applied to an object as it moves along a path. By definition, the work performed along the straight segment from P to Q by applying a constant force F at an angle theta is this here. Now, when the force acts on an object moving along a curve C, it makes sense to define the work performed as the line integral along C of F dot dr. We can use line integrals to define what is known as the flux of a vector field across a plane curve. So instead of using the tangential component of the vector field, we use the normal component of the vector field. Given an oriented curve C in the plane, we define the positive direction along C to be the direction going from left to right relative to the positive direction along C given by the orientation. We let n represent a unit normal vector in the positive direction across C and define the flux of F across C as capital Phi of Fc is the line integral along C of F dot n ds. Now, to actually compute flux, let R of t equal x of t, y of t, for a less than equal to t less than equal to b, be a positively oriented parameterization of an oriented curve C. Now, R prime would be x prime comma y prime, and this is tangent to the curve, pointing in the positive direction along C, and the vector n equals y prime negative x prime is orthogonal to R prime and points to the right. Let n be a unit vector in the direction of n. Now note that n and R prime have the same magnitude, so it follows that n would be capital N over the norm of R prime. With this, the flux would replace F dot n with F of R dotted with n over the norm of R prime times norm of R prime dt. This becomes now the integral from a to b F of R of t dotted with n of t dt. We'll be studying a different kind of flux a little bit later, the flux through a surface. But for now, that will conclude line integrals.